Hello everyone! In this video, I will demonstrate how you can use a GPS module with ESP32 using MicroPython. What I have here is a GPS module from GorillaCell ESP32 Development Kit. This module contains the E108 GPS module from Chengdu eByte Electronic Technology. GPS is an acronym which stands for Global Positioning System. GPS provides positional data, navigational data, and timing data services. Data coming from GPS transmitters allows users to calculate the three-dimensional position called coordinates, which are the altitude, the longitude, and the altitude. I have here a spare GPS module from GorillaCell. This module can be interfaced to a microcontroller using serial UART communication interface through this 4-pins port, or use it directly with your computer through this Type-C USB port. Let me connect a Type-C USB cable and let me open a serial terminal in my computer. I will select the correct serial port which is connected on COM18. I will use a baud rate of 9600 bits per second, 8 data bits, 1 stop bit, no parity, no flow control, and so on. I will hit OK. And as you can see, it returns GPS data to my serial terminal. I will stop it and let's proceed to the actual demonstration. This module has 4 pins which are GND for the ground pin, VCC for the supply voltage, TX for the UART serial transmit pin, and RX for the UART serial receive pin. In order to follow this lesson, you will need an ESP32 development board, a GorillaCell ESP32 Shield, a 0.96 OLED display, a 4-pin DuPont jumper wires, and of course, the GPS module itself. In using the GorillaCell ESP32 development kits, the following should be observed. When attaching the DuPont wires to the GPS module, the color coding should be such that black is for the ground, red is to the VCC, yellow is to the TX pin, and white is to the RX pin. While when attaching the other end of the DuPont wires to the GorillaCell ESP32 Shield, match the colors of the wires to the colors of the pin headers, such that black is to black, red is to red, yellow and white to the yellow pin headers. For this lesson, I choose GPIO25 and GPIO26 to be connected to GPS module, TX and RX pin respectively. For the software part, I prepared here one example source code for this demonstration. And in order to use this GPS module, we need an external driver library. Thankfully, I found from GitHub, which is from Calvin McCoy. I copy this MicroPy gps.py to my Tony IDE, which I have here, and save it to MicroPython device root directory by clicking the File menu, select Save As, select MicroPython device, and save it as MicroPy gps.py. Since we are using here an OLED display, we also need a driver library, which is this ssd1306.py. Save it to your MicroPython device root directory and click OK. If all things go well, you should observe the following in your MicroPython device root directory with the boot.py, MicroPy gps.py, and the ssd1306.py. Now let's go to example number 1. So basically, it starts with importing the pin class from the machine module in order to use the ESP32 pins. Then import the soft I2C class from the machine module in order to use a soft SPI interface for the 0.96 OLED display. Then import the UART class from the machine module in order to use a serial UART for the GPS module. Then import the MicroPy GPS from MicroPy GPS driver library that we saved in our MicroPython device root directory. Import also the SSD1306 I2C from SSD1306 driver library. Now here, we created a UART object named UART with an RX pin to GPIO25, TX pin to GPIO26 with a baud rate of 9600. Then created a micro GPS object named GPS. And for the OLED display, we used the soft SPI connected on GPIO22 for the SCL, GPIO21 for the SDA using a soft SPI module named I2C. And using the I2C object, we created a 128 by 64 pixels with an address of 0x3c and named it as OLED. Then I also used the built-in LED which is connected on GPIO2 and name it as LED. Now in our main loop, we read one line from the UART. Now for every character in the buffer, we parse the GPS data, which here, we print to the REPL the GPS timestamp, the GPS date, the number of satellites, the altitude, latitude, and longitude, and the horizontal dilution of precision. And here, we update the OLED display, which are trimmed down so that it can fit to the OLED display. And after that, we toggle the onboard LED. So let me click the run button to execute this one. As you can see in the REPL, we can observe the universal timestamp here, the date today, the number of satellites that is detected, the altitude, the latitude, longitude, and the horizontal dilution of precision. We can also observe here in the OLED display, we are displaying the date, the number of satellites, the altitude, latitude, and lastly, the longitude. We also toggle the onboard LED here. So that's it for this video. I hope you found this helpful. As always, the source code that is in here including other information can be found in the companion blog post for this video. tech2tinker.blogspot.com. Links in the video description. If you have any concern regarding this lesson, please write your message in the comment section. Please give this video a thumbs up and share this to your friends so that it can reach more people who might benefit from this. Please don't forget to subscribe so you will not miss video contents uploaded in the near future. Thank you and have a good days ahead. See you next time. God bless.